So let's get going. Good afternoon. Welcome to today's special asset colloquium by Soumik. He's from University of Chicago, and special because both he and Jaykumar flown from ICTS Mumbai, Bangalore, and they need to be arranged as a special because he is leaving probably a week later. And also welcome to this particular series of asset colloquia, which are all part of kind of celebrations because asset is celebrating 40 years of its existence all of this year. And it's great pleasure to have Soumik here on this very particular special year. Without taking more of your time, I now invite Jaykumar to formally introduce speaker of today. Thank you.
Welcome, everybody. Our speaker is Soumik Ghosh from the University of Chicago. He's a graduate student in the computer science department there. He moved there 3 years ago after finishing his master's at the University of Waterloo. And before that, he did his bachelor's from Jadavpur University in 2018. So welcome, Soumik. This is not Chicago, but it feels as cold. Yeah, please come.
Thank you so much for a very kind.
Does it work?
Does it work?
You don't necessarily have to stand.
Okay. Thank you so much to Professor Radhakrishnan for a very kind, for his very kind words. And thank you so much for hosting me here. Today, I'm going to talk about complexity foundations for NISQ devices. Feel free to pause me to clear up any confusion that you might have. Let's begin. Let's try to see what these words mean. The starting point of my talk is that quantum computers are here. For instance, Google had their first quantum speed-up demonstration in 2019. This was followed up by a series of companies and places which tried to replicate Google or come up with their version of quantum speed-up demonstrations. So there's a lot of quantum computers right now, and there's a lot of entities claiming that their quantum computer does some task much faster than classical computers. However, there are some caveats here though. What are those caveats? Well, the quantum computers right now are very noisy. We will get to what noise means after a couple of slides. But for now, let's take it qualitatively. So the systems we have right now, the quantum systems, they have a lot of noise. And secondly, they have limited system sizes. The number of qubits, that is like the quantum version of a bit, that's like 50. Google, I think, has 70, like very finite system sizes, very finite numbers. So this is called noisy intermediate scale quantum computation. Noisy because of the noise, and that phrase because we have limited system sizes. This phrase was popularized by John Preskill in just concurrent to when Google had their first quantum computer, 4 or 5 years back. So what can we do with these computers? Clearly, they're not going to change the world. They have a lot of limitations. But the question still remains, can we demonstrate some quantum speed up with these computers? Something that these can do that classical computers can't do. That's the broad motivation of this talk and a line of research. Well, let's loop back. What is our goal again? To say it again, we want to demonstrate that there's a task that these quantum computers can do much, much faster than their classical counterparts, the state-of-the-art classical computers. So what would be some desirable features of such a task, qualitatively, at a very high level? Okay, so what are some nice features of such, let's say, like such a quantum speed-up demonstration? Well, one thing that it should have is that, like I said, these devices right now, they have lots of caveats, lots of limitations, but these devices should still be able to solve this task, right? Secondly, classically, this task should not be tractable. Like, there should be a clean separation between the power of classical computers to solve this task and quantum computers. And thirdly, there's one more point. Let's say someone claims that they have a quantum computer that solves this task. We should be able to verify that this person is actually correct pretty fast, pretty quickly, with minimal trust in their quantum device. This is quite important. There should be some way to verify these claims of quantum supremacy, quantum speed up, because we may not trust the entities who have these quantum computers. Are these three features clear? Any questions here?
What the figure indicates on the right?
Oh, it's like some no, this is like some paradise, let's say, the best things that we want, the best case scenario. Like, yeah, like hopeful, let's say. The picture, it manifests hope. Okay, but real world has again. So what is the current goal of quantum advantage? These are the goals that we want, but what is it that we actually have? So current tasks that these quantum computers can solve, these NISQ computers, these are actually pretty contrived. These are hardness of sampling from certain very contrived, complicated distributions. That's in some sense tailor-made so that the quantum computer does get a speed up. What are some of these distributions? That's something that we'll see in the next slides. But yeah, these tasks are not like real world applications. Like, these are like something very contrived where we somehow want the quantum computer to succeed and we are starting from that prior and designing the task like that. I will come to that, but so far, no. So far, no. Like, you can map some problems, like we will see something much later in the slides, but then there are many caveats there as well. Let me come back to your question later. Any more questions? Okay, secondly, we don't have clean proofs that classical computers fail at solving these tasks. What we do have is a sequence of results that suggests with strong priors that maybe classical computers indeed fail for this task, but nothing has been cleanly proven yet. There's still this gap. And thirdly, we cannot really verify that someone has indeed, like a quantum computer has indeed solved this task in polynomial time. Verification is still like a very painful task, takes a long time. So this is what we have.
When you say complicated
Probability distributions, yeah. Yeah. Questions here? Okay, then, yeah, the fourth point, which is like a big caveat, is that none of the devices we have right now are scalable. If we keep increasing the system size, then the noise that you have, that just completely destroys your quantum signal. It becomes pretty like worthless. We'll see this in much more detail. But these are the limitations right now. What I'll do next is walk you through one task that's really popular. And that has been implemented in a lot of these demonstrations. This will be a good segue into later, like more real-world tasks, which will come much later. But this is like the starting point, let's say. This is what, for instance, Google did in 2019. So the task is random circuit sampling. Concretely, what is this? So the input to the problem is the description of a quantum circuit on a 2D lattice. It has a certain depth, and the gates are all nearest neighbor gates, depending on the location of the lattice points. And all these gates are drawn randomly from a gate set. Ideally, they would be drawn hard randomly, but companies have finite sized like gate sets, and they try it randomly from there. And the output, what we want essentially, is to sample from the distribution that's specified by this circuit and measurement in the standard basis. So you want to sample from the distribution, which is given by the circuit applied to a fixed reference state, 0 to the n here for simplicity, and then we measure in the standard basis. Measurement is a process by which we, like from a quantum state, we get a probability distribution, like sample from a probability distribution. As you can see, and this is what Google did, like I said. Like the thing that you can see is that this task is easy for a quantum computer. Why? Like given the description of the circuit, you just run the circuit and then measure it. That's what a quantum computer is designed to do, like run quantum circuits. So this is, yeah, that's what I meant by contrived. Yeah.
So what is the input? The input is the circuit description or just this?
The circuit description. The circuit description meaning the location of the gates at each position for this lattice and for each depth instance.
I'm sorry. This circuit description is given as a sequence of bits.
As a sequence of bits, yeah, like a classical string, let's say. Yeah.
But I mean, the description is randomly generated because
is randomly generated.
But then the quantum computer is supposed to adjust its gates to conform to
to conform to the specification. Yeah, and since there are only polynomially many gates here, more or less, and so by like just reading this bit string is like this will take like just polynomial time for a quantum computer, and then the quantum computer like will just run this circuit.
Suppose it says that apply phase gate, where the phase value is some 20-bit number.
Right. So the gates.
So then will the quantum computer have to somehow realize this particular phase gate using the gates that it already has?
Using the gates it already has, but for these companies at least, the gate sets are very simplified. Like so, like when we like just specify the gates by a classical string and then tell a quantum computer to run it, then that process is like polynomial time. That process can be done very quickly. That's how they choose these gate sets. Like
fixed reference state here refers to that 0 to the n.
Yeah, 0 to the n. But this could be something else as well. This is like a fixed, yeah.
When we talk about the performance of the quantum computer, it's straight from the input, including the transpilation and the actual running of the circuit, or do you make a distinction?
No distinction. Like this whole thing, like the whole time, let's say taken to like decode, like the thing that like the gate set, like decode the sequence of gates give. Yeah, that part can still be done classically. The the place where the quantum computer gets a speed up is in running this circuit and measure it. Like, yeah,
That's the only time.
that's the only time where there's a clean separation, or clean, like quote unquote, which we'll like just see later. But that's the place where the quantum computer gets a speed up. Yes.
The problem you didn't keep the fact that the gates are drawn back.
Yeah, I didn't need. Yeah,
The input is given a 2D grid. And
Yeah.
You're told which are the gates
exactly. Yes.
which are connected, and you're
Yeah.
told which are the gates there.
Yeah,
That's
precise.
coming from that a possible gate is coming from a fixed constant size thing, and then for each gate location, you're told which are the inputs, which are the outputs.
Yeah, exactly.
That's the input.
That's the input.
And your output is you want to sample from this.
Output is I want to sample from this. Yeah, yeah. For the specification, like I didn't need the fact that these things were like drawn at random. Like that fact will play a key part in like the complexity separations basically. And secondly, that like the fact that the gates like are drawn at random and then like and then we run the circuit, this is something that's doable by the hardware of these companies. That is like conveniently doable by these companies in some sense. So that's how, like, that's why they chose this problem. Like their hardware is tailored for these types of tasks. More questions?
What is the nearest neighbor gate?
Oh, nearest neighbor just means that the gate will act on its neighbor. Like, so say like each lattice point is a qubit. And a qubit in this grid has like 4 neighbors, right? And the gates that you choose have to be acting on just like that qubit and one of its neighbors. It can't be that the gate acts on like a qubit that's spatially separated farther from that particular qubit you're considering. So the gates will all be very local, confined to the neighbors of qubit. More questions? Okay, let's see the next slide. So what is the current hope? The current hope is to find a Goldilocks system size. What do I mean by that? So I want to like do this task of random circuit sampling for some fixed system size. For instance, Google had like 53 qubits, then had like 70 qubits later, such that when you have noise, we will see how noise comes in. Some quantum signal is still preserved. Like noise doesn't make this problem very classically tractable and like very classically trivial. Why do like the concern that noise might do that? That's something that we'll see later as well, because noise does do it. So the hope is you get like do this random circuit sampling at some finite sized system, such that like there's still some quantum speed up in this whole task. And the verification shouldn't be too complex. So what do I mean by verification here? Verification here at a high level it means something like, say someone claims that they solve random circuit sampling. They give you a bunch of samples and say that these samples came from some quantum circuit C, let's say. How do you verify that that is true? There's no easy way of doing it right now, but there are some benchmarks that we will see. The things are still pretty hairy, but like there are some ways. It's like for finite systems, such as things are still not too complex. Some statistical tests, precisely, yeah. Some statistical tests. And the third hope is that the state-of-the-art classical samplers, there's a lot actually, those don't work. That's what we hope. Like that's how we cross our fingers. And the worry here, and the good part as well, is that classical simulators, classical samplers, these keep getting better and better. And these keep getting very non-trivial, but so do the quantum demonstrations. So for instance, Google came up with their thing in 2019. Then there was a huge number of classical simulators that claimed to be spoofing what Google did. But then recently in 2023, Google ramped up the system size to 70. And yeah, so there's like a fight, like a tussle between quantum and classical. Not clear who's victorious. But one good thing that has come up, come out of it is like, because now there are these like clear quantum advantage demonstrations to spoof, people have much more motivation to study these very non-trivial like sampling tasks and like designing better like classical samplers for these tasks. And like I said, this task has already been implemented in many devices. 2019 Google 53 qubits, depth 20. Then a Chinese group followed it up with 60 qubits, depth 24. And then Google recently had 70 qubits, depth 24. This is the state of the art. Sorry? The thing that is left, or depth basically means how many layers of like gates that you apply. So like you have a 2D grid, let's say, like you specify some gates and like these nearest neighbor gates, and then you just like have like more such like specification, like more such layers, and so you keep doing that, like a 3D circuit in some sense, if you can imagine. Yeah. Yeah, precisely. So that's let me reply with a bit more nuance. So note that there's a type mismatch here. So what I would be talking about for the rest of the talk is some complexity theory guarantees of hardness, but these numbers are like these are fixed numbers. It's not clear what complexity theory would even mean here. But we still try to bridge the gap in some sense and say that like, yeah, so for this, if you scaled up like these things and like saw the behavior of how the noise is decaying or something, then maybe like you can hope for some quantum speed up at some large limits. But like these are finite sized, these are finite sized systems, and that's what I meant by NISQ. Yeah. Sorry? What can they do? Like barring, let's say, this contrived task.
So this contrived task they can do on.
Yeah, they can do. Yeah, this contrived task, these devices can do. Yeah. If they can do more, that we will see.
It's this difference to 3D devices.
Yeah.
That is physical devices. So what is the significance of depth?
That's a great point, actually. So the significance of depth is that many of these complexity theoretic hardness results, they kick in at large depths. Like when you are trying to prove that these models give you some quantum speed up, you need pretty large depths, basically. So it's not clear if you have like shallow depth circuits, it's not clear if you get like these like hardness results. But like once again, the caveat is the type mismatch. Like when you have two numbers, it's not exactly clear like how the complexity theory kicks in. But like still. Okay, why is this task of random circuit sampling, why is it believed to be hard? Let me give you a brief sneak peek into the how the hardness proof works. Now consider two problems. The first is what I call a classical sum problem. So given a function f, 0, 1 whole to the n to 0, 1, compute like sum over x, that function of x. And let me distinguish this with another problem, deceptively similar looking, but very different in complexity. I call this the quantum sum problem. So it's the same function f with a very minor modification. Now the range is -1 to 1, like -1 or 1. It's not like 0, 1. And Same problem, like compute sum over the functional value of the domain X. So what you can figure out is that both of these problems are sharply hard to compute precisely. What is sharply? For the purposes of this talk, let's just say it's some complexity class that's not believed to be solvable in polynomial time. It's like counting the number of satisfying assignments to a Boolean form. Both these tasks are hard. They capture the power of sharply problems. However,
all that you are given is checking for an input string if they have to.
yeah, like a query black box access to the function. Yeah.
This way to say F is given as a circuit.
Yeah. And yeah. Yeah. So you're just like just given the circuit to, then too it captures the power of the fact that like the thing we're just doing is counting the number of the number of strings for which a Boolean formula says yes, like in both cases. Okay, the picture gets really subtle though when we're considering calculating it not precisely, but we have some tolerance. For instance, let me slightly modify the problem. Approximate classical sum, but say with multiplicative precision. I want not a precise computation, but something like this. I want to compute a value that's close to multiplicative precision, that E. Interestingly, this problem no longer remains sharply hard. By a standard technique in like complexity theory called Stockmeyer's counting argument, it can actually be put in classical polynomial time with this black box. And this is like this class is a part of the polynomial hierarchy. And it's strictly simpler to do than the precise computation case, given the fact that the polynomial hierarchy does not collapse. This is like complexity theoretic hint that this task probably is much simpler than this precise computation that we just saw. Any questions here? Yeah, polynomial hierarchy collapses, meaning so polynomial hierarchy is defined to be a bunch of complexity classes, like progressively getting like these classes are believed to be progressively stronger, and collapses mean these classes just collapse to the same class. Like for instance, if this is true, then the polynomial hierarchy would collapse to its third level. So like you have these like progressively stronger classes, but the thing is, if this holds, then the whole hierarchy just collapses to the third class in the hierarchy. And that is not believed to be possible. Questions? The epsilon can be like 1 over poly, like it's like pretty like robust to choices of that parameter. For a wide range of choices, no. It can be like small. Like it could be like that thing could be like a constant as well, and this thing like and this sketch will not change. More questions? Additive approximation. Let's come to that in like a few slides. Additive approximation. Yeah, precisely. That's a great point. Let's come to that in a few slides. More questions? Okay, then let's see a second problem, approximate quantum sum. So same problem, but the specification now is that the function has like -1, 1, like the function maps to -1 and 1. What's the complexity of this quantum sum problem when we have multiplicative precision? This still remains sharply hard. Intuitively, why? At a very, very crude, very high level, the reason why this is happening, in some sense, like in my mind at least, is because of those negative numbers, because of these cancellations. And so, like, say, naively, what you might try to do is to like write this sum down as like a positive part, like with a negative part, and then apply this classical procedure to like compute each part separately and then subtract. Like this, like classical multiplicative precision, that compute. But that will fail because that doesn't preserve the sign. There's like a lot of cancellations going on, lots of negative numbers. That really makes like calculating this sum very complicated, despite that tolerance. Questions?
The way you think about the approximation is the mathematical procedure.
Like a randomized procedure in what sense?
Guessing that you figure out something exactly from this type of view.
Right, right. Yeah, that I think is how the reduction works. Like the yeah, that's the high level picture, I think. Like yeah.
It's like cancellation.
Yeah, the cancel. Yeah, exactly. F here is a given function. Like you can, just like given a description of f, like you try to.
Is there a way to understand why the same algorithm which worked when your range was 0 to 1?
Yeah. Say we do this. Say we separate this sum into a positive part, and then say we have this classical sum procedure to like compute that positive part. Do the same for the negative part, and then say we subtract. So nothing goes wrong if one of these parts is much larger, and this sum is basically this sum basically looks classical. But like say both the positive part and the negative part, say they are similarly sized. Then when you do the subtraction, then the sign might flip. And this, like computing the sum to this precision, this needs to preserve the sign. Like you can just see from the problem statement. So the sign flipping will be really bad. So there are these worst case functions for which that classical procedure that breaks really badly because it just flips the sign. Yeah, precisely. Even just finding the sign remains sharply hard. That's the proof of like say you start from there, the fact that just finding the sign, that's a hard problem, and then you do a binary search and then you just prove this problem. So now let's state some facts. Let me go over them quickly because of the lack of time, but take my word for this. So one fact is that if there's a classical sampler from a distribution, then something very similar to what you just said applies. Like you can write probabilities of that distribution in terms of a classical sum. Like that's what the Stockmeyer thing does in some high level sense. So, and the second fact is probabilities of certain quantum circuits can be written as quantum sums. That's why the term quantum sum in the first place. So what do these two facts tell you? These facts tell you that if you actually have a classical sampler from these circuits, these quantum circuits, then the polynomial hierarchy collapses. And that's believed to be a contradiction. Yeah, these are worst case results. Yeah, precisely. Let's get to the
all interesting.
Yeah, true. So this is just a complexity theoretic statement so far. This has nothing in the, this doesn't look back to the real world yet. That will happen very soon, but not yet.
But able to clarify, from what you have said, it is not quite well. So what we think is every single function on every interesting function was right to the output of the function. Okay, then
Yeah, so that fact is true actually. Each quantum sum, like a quantum sum, like the thing that you just saw, that can actually be written in terms of the probability for a specific quantum circuit. The structure of the circuit is quite simple. It's like some sort of like they call this Fourier sampling circuits. But each quantum sum does map to a quantum circuit. That part is true.
but that is required.
Yeah, that is required. Yes, true. That is required. More questions? Okay. So now let me come to a few caveats that you have raised already. The first is these are like worst case circuits. So each quantum sum, like I said, can be mapped to a quantum circuit. But the whole set of quantum circuits, it's not clear how to write the probability of each as these quantum sums. So how is the typical behavior? That's quite significant for like random circuit sampling because that's what we're trying to feel. And the second is, this is for precisely sampling from the distribution. What happens if we want to sample, like say have some total variation distance tolerance? Say we want to sample from distributions that's like close in total variation distance, but not the precise distribution. That seems to be a more realistic requirement in some sense. And this part is not actually known. There's no provable results here, but there's a sequence of works that are trying to get better and better. But we don't know this yet, like strictly speaking. What do we know though? So let me first talk about this problem. I call this a delta random circuit approximation. So I give you the description of a quantum circuit C. So I want to compute the probability of 0 to the n, like seeing 0 to the n when I sample from this circuit. But I don't want to compute that precisely. I have some tolerance delta. And the thing that I want is Q that's close to the precise value till delta. What we can prove, I'm not going through the details here, is that one sufficient condition to rule out classical samplers that don't precisely sample but have this total variation distance tolerance is to prove that the task above remains hard up to delta equal to this 2 to the minus n, and that being the number of qubits. Questions here? Okay, so have we reached this stage? Like, can we prove that this task remains hard till this value of delta? And the answer is no. Like I said, there's a series of works that are getting better and better. M, to remind you, is the number of gates in the circuit. So it started from 2 to the minus poly m. This is the first work that rigorously tried to quantify some of this complexity theoretic stuff regarding this sampling type, like sampling type demonstrations. This is Boland, Pfefferman, Nidke, and Fazinard. And then it kept getting better and better. Where we are right now is 2 to the minus m. And this is by Crovey. But there's still some way to go from there to 2 to the minus m. Questions up to here? M is the number of gates. M is the number of gates. And this is the number of qubits, N. The number of gates. Yeah. Okay, so this is the state of the art. But I did some switch. This is coming back to the question that you had. So multiplicative precision is something that so I motivated the complexity of these problems with respect to multiplicative precision. Then I just switched to delta, which is not multiplicative. So what is going on there? And the reason to make this switch is in some sense because this follows from the proof techniques. And why is this reasonable? So we had worst case hardness, and we were trying to apply that result to rule out to prove hardness for typical circuits. So generally we start from the contrapositive, we say there's some procedure to solve the task for the typical case, and then we do something like polynomial fitting to try to show that that implies that the same task is possible for the worst case, which is a contradiction. And so we pick up the delta at some point there. And this is something that I don't go into in the talk, but here I'm trying to motivate that doing this makes sense. Why? Because the reason it makes sense, the places where it makes sense is distributions where each probability is large enough such that the delta doesn't just kill off the quantum signal. And there's a name for this phenomenon. It just means that the distribution is not too concentrated with respect to some bit strings. It's mostly flat relatively, no matter where you look. Questions here? Sorry? Yeah, say the delta is too large. Say the delta is something let's say 1 over poly. But let's say the probabilities that you have for your quantum circuit, they are say 2 to the minus n. So then the task becomes trivial. So the probabilities, there's a tussle between the delta that you saw, like a tussle between that, the relative sizes of the probabilities, the tussle between that and delta. And so both need to be reasonably chosen, both need to be quite reasonable for this task to make sense. Questions? Okay. And what we can say is that noiseless random circuits of high depth, they satisfy this flatness property. Most probabilities for these circuits are sufficiently large. And their distribution is called something like the Porter-Thomas distribution. And it's the look of it is something like this. So 1 over 2 to the n is this. This is the flat distribution. And the probabilities are slightly biased from 1 over 2 to the n, some probabilities, and some are slightly lower. So most probabilities are pretty large. That precision, those things can just be swept under the rug because that doesn't kill off any quantum signal here. Questions? It's the probability P, and the vertical axis is how many bit strings have this probability. And so It just means that all the probabilities are 2 to the minus n.
Yes, 60 is your two.
Yeah. And so like we can prove this Porter-Thomas property for high depth circuits. That's where the depth is coming, like for these proofs. That's not true for shallow depth. It has some weak dependence on the gate set, but there are these papers which show that for like most reasonable gate sets, like say for sufficiently high depths, like you tend to this distribution. Yeah.
X in the exponential, I should read it as the binary. I mean, X is a string.
Yeah, like say so this is the PDF of the distribution, and so like read it as like some number for like
Quantum circuit is sampled. It produces a string.
it produces a string. Yes.
That I should think of as X.
Yeah.
And when you write X as a number on the right, I should think of it as a binary number that string represents.
Yeah. So this is like a continuous variable, like approximation to like what is going on. Because like when you do this sampling, like you will like the thing that you'll get is like a discrete distribution. But this looks like this Porter-Thomas, like at very high, like large N limits. Yeah, precisely.
That has a very good property.
How? Like the property being like what? Like qualitatively?
That means I say that that means that the random variable is defined. Then its value beyond 5 is as if it's
Right. Yeah, that's true. So the strings that are higher than, let's say, some mean or median, like some or mean or median probability weight, that just depends on the circuit chosen. That doesn't depend on the threshold. Yeah, it has that memoryless property. Yeah. Okay, so let me, like for the lack of time, let me quickly run through the next few things that I wanted to discuss. The first is verification. How do we verify like this, like the fact that some quantum computer sampled from this distribution? Okay, note that a signature of Porter-Thomas is that some strings are slightly heavier than the rest. Like there's this slight bias from like the fully flat distribution. And which strings are heavy? That just depends on what circuit I just sampled randomly. Nothing else. And so in some sense, qualitatively, like without running the circuit, it's not clear how to decode those heavy strings. And that's exactly the statistical test. Like that's the property we leverage to design a statistical test. And the test is something like this. Say someone claims that they sampled from this distribution, like with respect to a circuit C. So they give you K samples. So you compute the probability weight that each of these K bit strings has on the distribution specified by the circuit C. And then you see if it passes that value. If it like passes that value with a high score, like 2 precisely, that's the score, like that's the signature for Porter-Thomas, then you say that that's like the correct distribution to sample from. And it's conjectured to be hard for classical computers to get a score more than more than something that decays like polynomial.
Test that can be performed.
Yeah, this is a test. Yeah, this is a test that can be performed, but not in polynomial time. This is a test that requires a lot of time. But this is some test that people do.
I mean, the bottom expression simulates the circuit, the PXI.
Yeah, the bottom expression is yeah. That needs that needs you to simulate the circuit. There's no shortcut there, and that's what takes you like a lot of time. Okay. What happens with, sorry. Yeah.
So what does this thing that generates it do? It should not only output this, but it's also give us proof that it has is a heavy element, or what should
No, it's not so much a proof. So say I get samples from say I get samples from someone I don't trust, who claims that they have a quantum computer. Their job is to just give me some samples. My job, like the job for the verifier, that is to run this test. And the claim is, if we pass this test with a high enough score, that is a certification that the samples came from a quantum computer.
What are all its inputs?
The samples, just the samples.
Samples are the
Yeah, the samples with the quantum side. Yeah, both the verifier and the guy just just doing the sampling, they know the quantum side. Yes. Yeah, that's the way to verify. Like if just brute force compute this PXIs, then just that takes, there's no polynomial time verification.
Read the last line. Calculated in classical exponential.
But then there is no
It doesn't satisfy. Like this is not a polynomial time verification test, but this is the best we have right now. Like there's no known way to do better yet. For these devices, finite system sizes, this can be done. Like 50 qubits, that's still that still takes a lot of time, but still can be done. I don't think there's I don't know actually, but I don't think so. This is some very vanilla benchmark test that people came up just to verify their tasks basically. There's no deep qualitative picture here. This is just some test that people have done. Test of errors. Let me. There are those caveats, yes, and that's something that we'll see. There are many caveats with noise. In fact, that's something that we will just see in the next slides. So let me talk about noise now. I have 3 minutes, I think, so I'll be a little fast. So let the noise model be uncorrected depolarizing noise, which is so each gate has this noise. Let's take this model for now because of its simplicity. What does depolarizing this noise do? This pushes you towards the maximally mixed state. And when you sample from the maximally mixed state, you get a fully flat distribution. And the convergence to this fully flat distribution, that is at a rate that convergence grows better and better with depth. And so for large steps, polynomial, super log even, let's say, the flat distribution, that itself is a good proxy for the distribution of these random circuits. So classically, sampling is trivial. Just flip some coins and those are your samples, and that works. The consequence is classical sampling becomes trivial at high depths, when you have this noise. But there's some hope of quantum speed up at log depth, right? Because for log depth, the total variation distance becomes some polynomially close to the flat distribution for some fixed polynomial. But what if I fine tune the precision? What if I try to sample from some distribution that's 1 over some finer polynomial close to the target quantum distribution? That could potentially still be hard. Did the motivation make sense? like at log depth, there could still be some small room where there might be some like salvageable quantum signal. Like the maximally mixed state may not be a good proxy for those finer precisions at log depths, like specifically at log depth. Yeah, so there was, yeah, so we saw this flatness property, like some slides later. Some flatness is required to make this switch between multiplicative precision to something like less robust. So it's needed for hardness proofs. But like a catastrophic flatness, like the fully flat distribution, for instance, that makes things classically that makes this sampling task trivial. So there should be like a Goldilocks zone here as well. And can we leverage these at log depth? But hopes were dashed. Like very recently, like last year, there was this paper which told you that random circuit sampling with depolarizing noise becomes classical polynomial time at log depth as well, no matter what polynomial precision you choose. So that's bad news for this quantum supremacy, like this like quantum speed up type business. And this was very recent. Yeah, and that made like this circuit sampling task simple, that made that circuit sampling task classically tractable, like when we had logged. And noise causes problems in verification as well. Like the type of problems, let's see. So for noisy circuits, this bias, this goes down as 2 to the minus d, where d is the depth of the circuit. For noiseless, this bias is 1. So the score actually would be 2 over 2 to that. And for noisy, so say the fully flat distribution, this is 0. And so the quantum signal is between 0 and 1. And Google saw 1.0001. And they were happy with it. Why? That's still much more than 2 to the minus d. So in that sense, their quantum signal was non-trivial. That was their justification. Sorry, typo here, 0.07. Yeah. That's a type, yeah. Yeah, so noise causes problems for verification. And let me briefly segue into something that these near-term devices can do, barring just sampling from these very non-trivial distributions. That is, these can be harnessed potentially to solve some problems, like some optimization problems. And how, the problem setup is as follows. Say I give you a Hamiltonian, and I tell you to find its ground state. And this is a CS way of looking at the same problem. There's some matrix, like you do the spectral decomposition, like you try to find the vector corresponding to the minimum component, for that, the minimum component for that spectrum. Did this task make sense? Okay, how do we solve this problem? One way to do it is that you start from a random guess state, which you model as a random quantum circuit. And then you run some sort of a gradient descent based method, and then you try to make the guess more refined. And you keep doing this. But noise causes problems here, pretty fatal problems, because noise means the distribution keeps tending towards the flat distribution. And the gradient becomes 0. This is called the barren plateaus phenomenon. So the whole process gets stuck. And this was fast shown rigorously. This paper was the one to show it rigorously, some years back. So noise is really fatal for these devices. Question? Okay, but there's still some hope. What are the hopeful places still? One place is that short depth quantum circuits, we don't have any proofs for hardness, but it's also not clear that sub-logarithmic depth random quantum circuits, they're classically simulable. The hardness proofs break, but so far there's no classical simulator too. So maybe there's some hope there. And the second place is maybe we'll get better methods to mitigate the noise. This is more longer term, but people are trying to do this. Like Google's recent papers have been on noise mitigation. And low noise circuits qualitatively, like this is something that I didn't get into for this talk, but like you can prove that circuits which have very low noise, these behave very differently from the scalings that we just saw. Like those results do not hold for circuits with low noise. Low meaning like going down in system sizes and not a constant. And let me conclude with let's conclude with a punchline actually. So we saw a model of noise. I said that this model was considered because of its simplicity. We saw that the model was depolarizing noise followed by a gate, like a gate followed by a depolarizing noise. But this is too simple. Like real hardware has all types of very complicated noises. There's like, these are called like non-unital noises. There's a whole bunch of them, depending on like the gates you have, depending on the measurements you have. And the behavior of these noises is very different from the depolarizing noise. So what happens when we actually consider these realistic noise models? We showed, like with a couple of collaborators, that when you have these realistic noise models, this phenomenon that I talked about of like this flatness property, that just breaks down. So the distribution actually does not converge to a flat distribution, no matter what the depth of the circuit is. So the hardness proofs break, but the classical simulators that we saw, they break as well. So the punchline is, for realistic random circuits, we do not know if the task of random circuit sampling is hard or not. There's no proof. But there's no proof that this can be classically simulated. This was our recent work. And we followed it up with like a simple corollary saying that there are no barren plateaus. But that doesn't mean that these types of variational procedures that we saw, they give you something like that's close to the result. This just means that the gradient descent method, which was failing for depolarizing noise, that doesn't fail for this realistic hardware, these noise models. Does that mean we get a quantum speedup? Well, no, the jury is still out, just because the hardness proofs break as well. Like we need new ways to prove hardness for these tasks. And thank you, that's my talk. And for a more comprehensive survey, please look at Bill Pfefferman's PCMI lecture notes, like on the same topic.
Question.
I want to do preparation quantum 20 for just bounded depths.
For bounded depth.
So I'm considering a bounded depth quantum step. So it's a bounded depth classical
circuit
Yeah.
for the purpose of sampling. Yeah, there we have unconditional lower bounds
There
for
we
classical
have-
circuits, right?
Yeah.
So
Those have been recently leveraged to prove clean quantum separations. This was like a work from last year. Yeah, for like bounded depth circuits, there are clean separations. Yes. But the dicey part is the separation breaks down when you give the classical computer more power, like say polynomial depth or something. But yeah, those have been leveraged. More questions?
Yeah, so if there are questions from audience who've joined online, please raise your hand or just unmute and say. No questions.
So let's thank the speaker for a very admirable effort to reach out. Thank you very much. And that's it. Yes, sir. Thank you. Thank you very much. It was very nice. It was a very nice.
Sure. I think, like, Thanks. Thanks.